Okay, thank you, Trifan. Okay, thank you, Dima. It's good to be back here at IPAM. Especially, this is the place where I started work with Jan Maas on optimal transport for fermionic systems. He had just finished his PhD in the Netherlands and had still some funds left over. And I was here at a workshop for kinetic theory, which was a different topic, but IPAM found him an office and we began our work together. My introduction to mass transport was through my friend and then colleague at Georgia Tech, Wilfred Gangbo, who is here and will be speaking later at the conference. And so this is a very good opportunity. Very glad to be here once again and to see many people. Okay, so I'm going to be talking about Gaussian states, Gaussian processes, and Gaussian quantum dynamical semigroups. This is the context in which I can say something about this problem that we're trying to study. And the Gaussian probability densities on Rn can be characterized in a number of ways. Two of the most important is that orthogonality implies statistical independence. Gaussian random variables that are orthogonal are statistically independent. And another is that the entire distribution is characterized by its second moments. Okay? Now, quantum analogs of these exist on algebras of operators on the boson and Fermi-on-Fock space. And the boson case is probably the most studied. It arises crucially in quantum optics and quantum information theory. Quantum communication is mostly done with photons, which are bosons, and so that case is very important. But there's also the fermionic case. And I'm going to be talking about quantum dynamical systems that are preserved Gaussians on Fermi systems, and this is connected with quantum qubit systems, as we will see. Okay, why is this not? Good. Okay, so let me say a little bit about just to make a connection between what's going on with the Fermi systems, which may be less familiar. Here's something that is probably familiar to many people. Whoops, got this thing going right. Okay, so let's take the Hilbert space L2 of Rn with respect to the standard Gaussian measure. Okay? Let M be a multi-index of non-negative integers, and let H, vector M, denote the corresponding Hermite polynomials, so just the product of the one-dimensional Hermite polynomials which are orthogonal to this. Okay? Then this L2 space decomposes into the direct sum of the polynomials of fixed degree n. We should have put a k here. The n, it should have been a k. So the n is right. This is put k here, okay? And then there are these functions phi which map Rn into the linear space, and you just take a vector and turn it into a random variable like summing by so, and the algebra generated by the image of phi is dense in the space. That's because polynomials are dense in Gaussian space. And then for any density matrix rho on F regarded as a state, is determined by its moments. So these are the moments, right? Okay, and this is well, in the physics literature, this is called Wick's theorem. It expresses the general moment in terms of what is the Pfaffian of this matrix M, which is the second moment matrix. Okay, this is a covariance matrix because these are mean zero. Okay, so this tells you what all these things. Alternatively, Gaussian states can be characterized in terms of the Wigner transform. For those of you who know about those, I won't say much more about that because we won't be using exactly that in the fermionic case. But a state is Gaussian if and only if its Wigner transform is a Gaussian probability density. So that's another characterization that might be familiar to many people. Otherwise, take this as the characterization. Okay? Now, a quantum operation is Gaussian if it takes Gaussian states to Gaussian states. And we'll be concerned here with quantum dynamical semigroups, and those are semigroups of completely positive trace-preserving operators. That's a quantum dynamical semigroup, and they will have the additional special property that they take Gaussian states to Gaussian states. Okay? Good. Okay. So for any Gaussian state, there is a canonical quantum dynamical semigroup that has that Gaussian state as its unique steady state and which satisfies the detailed balance condition with respect to sigma. That means that each of these PTs is self-adjoint for the inner product induced by sigma via the GNS inner product. So that sets out a special one. And there's an explicit expression for not only the generator, but the semigroup itself. give in terms of a sort of bosonic Mehler formula. You can do a Stein-spring dilation of the whole semigroup all at once, okay? And we'll see how that works out in the fermionic case, okay? And let's consider 1 degree of freedom to make the formulas easy to write down. And then there's this 1-parameter family of centered Gaussian states. The parameter nu is in 0 to 1, so that this geometric series is summable, which makes this thing trace class. K denotes the orthogonal projection onto the span of the kth Hermite polynomial, okay? And let rho t be the canonical Gaussian quantum dynamical system generated by this. Okay, now we'll be concerned with approach to the steady state. In this case, it's equilibrium because that is actually a thermal state, an equilibrium state. And so this is a quantity called the relative entropy. And I'm sure, as most people know, it controls the distance between rho and sigma. It dominates the square of the 1/2 the square of the trace class norm between rho and sigma. So if this goes to 0, rho is converging to sigma. Now, this equality follows because the sigma is the steady state for the rho, so I can put a PT here without doing anything. And then this is the famous data processing inequality, which says that whatever quantum operation you apply to 2 quantum states can only decrease the relative entropy, making them harder to distinguish. Okay, so the relative entropy is decreasing. And the problem Jan Maas and I worked on was how fast can these things decrease? Can we control this? And one of the key examples in our second paper was we found this rate of decay, which is the sharp rate of decay for these canonical Gaussian processes. This had been conjectured earlier by Huber, Koenig, and Verschanina, and they showed that this rate is the best possible because there's a Gaussian state that saturates this inequality. So you can do calculations with Gaussians, and so they tested if they put in the Gaussian steady states and worked out how fast do they decay, and they found the worst case for Gaussian states, and this was it. There's a missing t here, somebody might tell me, okay? Yeah, I saw some puzzle books, okay? It's decaying at e to the minus t, not, okay? So that's what the t over here connects up with that. Okay, so they had showed this, that the worst possible among Gaussian states where you can compute everything is this rate, again missing the t and again missing the t, okay? The cut and paste propagates these things. And so using our optimal mass transport method, John and I showed that in fact, the soup over general states was this, okay? Now consequently, what this result said, what these two things together say, is that the rate taking the soup over Gaussians is the same as the soup in general. So you only have to do calculations for Gaussians. It would be very nice to know that something like this is true in general. This is a theorem of the type Gaussian kernels have only Gaussian optimizers. This is something that was studied extensively by Elliott Lieb in the classical case. It's been studied fairly extensively in the case of the boson quantum operations for its role in optics. And a number of people have worked on this. Only partial results are known there, beautiful partial results. I won't go into the boson case because we will be talking mostly about the Fermi case. But this is something in general for not only for the relative entropy, but other kinds of quantum operations. You can look at the LP or Shatton class P to Q norms, and people expect, I think it's a widely believed conjecture, that the same kind of thing Lieb's classical theorem generalizes to Gaussian quantum operations in general, that Gaussian states should have, and this is closely connected with the product property and so forth. So it's interesting that this can be proved, at least for these special classes of things, in the context of, for quantum dynamical semigroups by the mass transport methods. Now, in the paper that Jan and I wrote, we did this not only for this Gaussian case for the bosons, but we treated the Fermi case as well. And the Fermi case really fits into our framework very nicely. I mean, you can see what inequalities you have to prove in the Gaussian case, but of course the Fock spaces for bosons are infinite dimensional. Annihilation creation operators are unbounded, and there are technical things that one has to sweat about, okay? In the fermion case, if you have n Fermi degrees of freedom, the Hilbert space is 2n dimensional. It's a finite dimensional space, and we're really in a nice familiar setting that is the setting in which much of quantum information theory is done in. The Hilbert space, whoops, let me just get this thing going. The Hilbert space that we're working with, this 2n-dimensional space, there are two ways to look at it. You can take C2, the n-fold tensor product of C2, okay, a qubit spaces. So this is the state space for n qubits, okay? And the other thing you can do is look at it as the Fock space. You can take the direct sum of the antisymmetric powers of n-dimensional Cn space. These are naturally isomorphic because they have the same, well, they're isomorphic because they have the same dimension, and they're naturally isomorphic, as we'll see. So fermionic Gaussian states arise naturally in the study of qubit systems, and we'll see how this works out. Okay, so the main question, which I'm not going to answer, is this. Is something like this, that you only have to search when you're computing or trying to estimate the rate of relative entropy decrease, and you have a Gaussian process, a Gaussian quantum dynamical system, is it true that you only need to look at Gaussian test functions to estimate this rate? Okay? I mean, if this was true, this would be very useful because as Huber, Koenig, and Vershini, their example, I mean, it's easy to, this problem, this soup is much easier to compute, even in the boson case. Okay? Great. Okay? So, in this setting, so we're looking at this now. Now, the Gaussian quantum dynamical systems that we're going to be studying here are ones that are not having any kind of detailed balance. In fact, they're not having any kind of symmetry with respect to any of the various inner products you can define. Something else that Jan Maas and I showed was if you can write the quantum dynamical semigroup as gradient flow for the relative entropy, then necessarily that generator of the semigroup is self-adjoint with respect to the BKM, Bogulyubov-Kubo-Mori inner product associated, which is a more general class. Unfortunately, there's no structure theorem, and another problem that's open is to show that there is a mass transport metric so that any such BKM symmetric quantum dynamical semigroup is gradient flow for the relative entropy. That is something I would very much like to know, but I don't have anything to say about that one. Okay? So I don't know how to answer this question, but there are a number of questions that attach to it that we will be able to address here. And okay, hopefully we're working towards getting an understanding of this bigger problem. Okay? When I was working with László Erdős, when he was my colleague at Georgia Tech, and we had job candidates come by, he would always ask them, "What is your dream problem?" Okay, and depending on how they answer, that was a very important question. But I would like to understand these kinds of questions. So that's certainly one of them. Okay, now there's a large literature on the exact solutions of models of the type that we're going to consider here. There's some names up here. Prozin, third quantization has been used that you can find in the theoretical physics literature. But there are a lot of some nice mathematical techniques that I don't know where they exist in the theoretical physics literature that enable one to get some exact solutions to work with in the context of Gaussian states. Okay, so we're going to be again working here with quantum dynamical semigroups that preserve Gaussian states for fermions. So I have to tell you what is a Gaussian state for fermions. Okay, so what does this mean? So fermions are built out of the so-called canonical anti-commutation relations. So the CAR, canonical anti-commutation relations, are any collection of n operators that satisfy this anti-commutation relation. So they anti-commute among themselves for the A's, and then the A dagger and the A. So the dagger is the standard physics notation for the adjoint, right? So that just means the adjoint, and I'm just writing it like that. So there's a construction of this thing. You can realize these things in a way that relates it to the spin chain thing. This goes back to Brouwer and Weil. It's known in the physics literature as the Jordan-Wigner transform, but Brouwer and Weil first wrote down this construction earlier. And here's how you do it. You take the Pauli matrices, so these are the standard Pauli matrices. Then these anti-commute among themselves, which is a good start. So then you form the sigma plus and sigma minus, which are these guys with the X and the Y gadget. And these are simply this, and they anti-commute among themselves. Now, to get them to anti-commute with each other, what you do is you put a bunch of sigma z's before the sigma minus, and then identities after that. So in the jth place, I put the sigma minus, sigma z's to the left or the right, okay, and then identities on the other side. Now, the point is that the sigma minus, which is built out of sigma x's and sigma y's, that anti-commutes with the sigma z. And so when you take two of these things, they anti-commute because in one case, the sigma minus or plus is hitting the identities and it commutes, but then the sigma minus is anti-commuting with a single sigma z, so you get exactly one minus sign. So this is the construction of Brouwer and Weil, and this gives us this family of operators. Okay? And there's a natural inner product which we'll use, so the tau denotes the normalized trace. It's natural to normalize the trace because you can take the n all the way up to infinity, and then the normalized trace exists in a C-star algebra of unknown algebra sense, but the regular trace, of course, does not. Okay? But everything here will be finite dimensional, but that's the reason you want to do that. Okay? The normalized trace makes good sense in the limit. Okay? And then there's the Fock space. Okay? And the connection between the two is the following. You take a vector psi in Cn, take some orthonormal basis, take the component of psi, and multiply this component times the aj star. I've switched from stars to daggers here, so star equals dagger. And so this gives you, this maps you from the vector space Cn, capital N, okay, capital N here, into the algebra. And then you can identify this wedge product with just the product of these anti-commuting things. And these anti-commute and these anti-commute, so it all makes sense, and this gives you this nice construction. So that's the Fock space, but we'll be working mostly with this spin chain version of it. Okay, and now if you've got, we came up with a particular construction, but it's going to be important in what follows that if you take any unitary matrix, you can do a unitary transform of these guys, and that gives you another representation of the canonical anti-commutation relation. So these are unitarily invariant. Okay. Now we've got the building blocks for Gaussian states. So Gaussian states are what you would think they are. This is usually not the way they're written the first time, but it's true. So the rho, you take a k, which is a quadratic gadget in the A and A daggers. So this is a self-adjoint operator if the k is self-adjoint, this matrix, and you exponentiate it and normalize it. So exponential e to the minus quadratic, that's what a Gaussian should be. So Gaussian states are also known in the physics literature as quasi-free states. Okay? Now the way this is usually written is in terms of normal modes. So you can diagonalize k, this operator k that's over here, and using a unitary, and because of what we just said on the last slides about unitaries, I can rewrite this thing in terms of the sum of normal modes. So I introduce these normal modes, which are the C's, the unitary transform of the A's, and then this operator can be diagonalized in terms of these. So this is called the number operator for the alpha state, and this is a projection by the canonical anti-commutation relations, and this is identity minus the projection. So these things add up by the canonical anti-commutation relations. So these are commuting projections. And so this operator k hat can now be written in this form in terms of projections. And now it's really easy to exponentiate this, right? Exponentiating identity plus a projection, what could be easier? So you work it out with the lambdas, and this is what you get. And so this is the general Gaussian state written in terms of its preferred modes. So if you diagonalize a Fermion Gaussian state, this is what it looks like. Okay, any questions? So that's...
Yeah. So if you translate that to the spin picture, what characterization of quasi-physics do you have then?
Well, I mean, for me, this is still I mean, these A's and C's are just operating on the spin space. I mean, I constructed them using this so-called Jordan-Wigner transform. So my A daggers are operating on the spin chains, Hilbert space.
Okay. I mean, it's somehow non-local in a way?
Okay, no, this is a very important, right, they're non-local, because, so this is a very, very good point, this will come up. When I did this Jordan-Wigner transform, remember for the AJ dagger, I put a sigma plus in the jth place, I put sigma z's all the way to the left and identity all the way to the right. So this is a non-local thing because it's got this chain of sigma z's all the way to the left. Okay, so so these are non-local. However, you will see that when we write down these generators, which is what I'm coming to, the locality is going to reemerge for the generators you look at. Okay, but this is a key point. So right now, there's this product of the sigma z's. So my sigma j, I mean, to make them be fermions, they've got to anti-commute. So they can't be local, or they wouldn't anti-commute. Okay? But nonetheless, it's well known, it's often used in the physics literature. This goes back to, I mean, Schultz, Mathis, and Lieb, or maybe even earlier, to rewrite things using a Jordan-Wigner transform to understand spin systems in terms of fermions. So there's a solution of the Ising model using this, it's the same idea. Okay, key point. Marius, yeah.
This is unfortunately for a couple of pages back, but you're concerning your dream. I remember Holevo had a very similar dream.
Yes.
And
mostly for bosons, I would say, but yeah.
Yes, but that was solved, right?
Well, there's I mean, I don't think for the entropy, I mean, this question is still open.
I'm just saying whether, these connections are made.
Yeah, right, it's not, right, it's totally not clear, and I'm going to describe the program, so we may be able to, what I would like to know is whether this is true or not, okay? And there's reason to doubt it, which I will explain later in the talk.
But it's anyway to be a good company with Holevo's dreams.
Sure, great company to be, right. Okay, anyway, so this is what the Gaussians look, oh, another, yeah.
Yeah, could you go back to the last page about the definition of the Gaussian state? As here you define the Gaussian state as the exponential of the operator, but this is only for the totally mixed Gaussian state, which means that this Gaussian, I mean, for the case that this Gaussian state is a Gibbs state of a quadratic Hamiltonian. How do you deal with the case that the Gaussian state is, how do you deal with the pure Gaussian states case? I mean, could you define the pure Gaussian states as the ground state of the...
Well, we'll go into a few more slides coming up, but I mean, this is, I see, it's not really a standard thing, but this version, as you vary the k, this version covers the full class of Gaussian states. Okay, let me explain how this goes. You'll see. Okay, so this is another way of writing them, which looks like this thing. So here's this maybe. So let rho be a Gaussian state. So all Gaussian states are characterized by the covariance matrix. So let me define this M rho to be the covariance matrix, which is this. So as I vary the M, I get all Gaussian states. Okay? Now this M matrix, by the canonical commutation relations, it's a matrix that is dominated by the identity and it's non-negative. Okay? Now if I define K equals log of 1 minus M over M, and the K hat to be this, then the rho is given by this K hat. Okay? So I mean, there's the K that gives me a general Gaussian state in terms of its covariance matrix.
Just to check, so this matrix is not necessarily real, right?
No, not necessarily real. Right. Okay? So there's a Wick's theorem also for this case. And so Gaussian states are precisely those whose non-vanishing moments are given by this. So instead of a Hafnian, which is what you get in the boson case, you get a determinant here. And so that's what this is. Okay? And great. Okay? Now the following is well known and easy to prove. If you've got a quadratic Hamiltonian, okay? If you've got a quadratic Hamiltonian and you conjugate a Gaussian state by the unitary group that generates, this is also a Gaussian state. And moreover, the covariance matrix is given by this unitary evolution of the matrix by this symbol. So H hat is the operator. See, H is an n by n matrix, and H hat is a 2n by 2n matrix. Right? So the evolution of this n by n matrix is given by this n by n unitary group. Here you're going on in the big space. So you can track this kind of evolution in the smaller space. So this is well known and we'll be ready to use this. So we're now ready to define a class of Lindblad equations. And the starting point here is the classical Mehler formula. So again, let the Gaussian distribution be this. And then for any continuous function, define this operation. So you take f of e to the minus tx plus, you notice that this squared plus this squared is 1s. We're doing a rotation in doubled coordinates, and then you integrate out y. So if you take t going off to infinity, the x gets washed out, the y is all there is, and you're just taking the expectation. This interpolates between the two of these things. This is a formula from a paper of Mehler in 1866, which is 2 years after Charles Hermite wrote down the did his work on the Hermite polynomials, and it's fun. This has closely connected with Hermite polynomials. This is a semigroup. You can do it directly, but you can do it also using the generating function for the Hermite polynomials. And if you apply the formula to the generating function of the Hermite polynomials using some standard stuff and expand, if you differentiate, you find that, lo and behold, if you take f of xt to be this pt of the f, the time derivative of that is given by this Ornstein-Uhlenbeck operator. So this semigroup involving this rotation solves the Ornstein-Uhlenbeck equation. This is Mehler's formula from 1866. Okay? Now, you can take the adjoint of this thing, and the adjoint will act on probability distribution. So just move this, take the adjoint over here, and it acts on rho. If you just work out what the adjoint is, you can see what it's doing. And notice in this, the one thing to notice from this formula is suppose rho is a Gaussian state. Well, gamma is Gaussian, so the product of these two Gaussians in two orthogonal variables, right? So you see this variable is orthogonal to this one, these two directions. So I'm taking the product of Gaussians on orthogonal subspaces. This is a Gaussian, and when I integrate it out, I'm taking a marginal of Gaussians. So if rho naught is a Gaussian, so is rho of x and t. So this is one way to see, which is relevant for us, that this semigroup given by this doubling of the variables, rotating and taking partial traces, takes Gaussians to Gaussians, okay, which is what we want to do, okay? Good. Okay, so now here's a Mehler formula for fermions. So we do the same thing. You double the variables, so you take your a's and you extend them by putting on some extra things so that you've got the CARs in 2n variables. And now you do a rotation with these things. So the a hat of t is you do these rotations. I've made this probably too complicated. You can put in different rates and the different degrees of freedom, but this is important for getting all the possible Gaussians out. So you can do different rates, okay? And then you can write this rotation in this form that we have over here by a unitary conjugation for a quadratic Hamiltonian. And then what you do is the following, okay? So you take the rho and the sigma. Now, the sigma, so the rho can be anything, but the sigma, being a Gaussian, is the product of quadratic operators. So that commutes with anything, right? So if you move it past, so this is something, the rho is something in the b variables, say, and the sigma is in the a variables. But everything comes in pairs, so when you move it past the b, you get two minus signs, so it moves over. So the product of two non-commuting positive operators is not even positive, it wouldn't be a state. But for that reason, this rho sigma is a bona fide state, right? This is the density matrix. Now we rotate it using this quadratic Hamiltonian, and we integrate out the b's, okay, trace them out, and this is also a quantum operation. It's essentially taking a partial trace, and so this is a quantum dynamical semigroup. We've done several things. We've attached ancilla, if you like, we've rotated it, and then we've taken a partial trace, which is the usual way of representing what a quantum dynamical semigroup does. And the point is that if the rho is Gaussian, so is rho sigma, and so this evolution takes Gaussian states to Gaussian states. And it also clearly, if you rotate the whole thing out, it takes you, the steady state of this thing is the sigma. Okay? So, and that's the steady states, and that's what it's going to converge to. Okay? Moreover, it turns out that this PT is self-adjoint with respect to the GNS inner product, so this construction gives you a semigroup which satisfies the detailed balance, and so this is this canonical semigroup that I'm talking about. So you give me a Gaussian state sigma, this is the canonical semigroup I'm going to write down that has that as its steady state, and it satisfies detailed balance. Okay, now, given any one of these Gaussian states, the Mehler construction provides, the Mehler construction provides us with this semigroup, and it gives us a continuous Steinspring dilation of the whole semigroup. So the generators of these semigroups can be written, of course, in the Lindblad form. And what are these things? Okay, you build them, all of these generators are built out of the following gadgets of linear combinations of these things with certain weights. And what is the W? The W is an operator here that implements the rating transformation. So it takes minus on odd things and even on even. Okay? And what it is it's nothing other than the product of all the sigma z's, which commutes with these things. Okay? So now this gets back to the question about the localization that was raised earlier. When you look at these generators, the AJs are not local, but when you multiply them by the W, you are canceling off all the sigma z's that you put there for the first time. And so if I do my Jordan-Wigner transform, so I have just the spins on the left, I'm going to cancel off all the sigma z's, and so on this last part that's left over, they will be local to that space. They won't be local to a single spin. I'll have a diagram that comes up next. But the generators are not simply the annihilation and creation operators as they would be in the Gaussian case. They have this grading transformation in it, and that's kind of important. Okay, so that's what these Gaussian processes are. And this might all look a little strange for these things, but these things really are Gaussians, and this was, for me, I mean, this was the problem that got me interested in this thing. I used to be a regular classical probabilist, and Leonard Gross, my mathematical uncle, student of Irving Siegel, I was a student of Ed Nelson, introduced me to his conjecture about fermion hypercontractivity. And the point of view of Irving Siegel was that fermion Gauss space really was a Gaussian space, and fermions and bosons should behave exactly the same way. Nelson had proved that if you take the Ornstein-Uhlenbeck semigroup, exactly the one we talked about earlier classically, it smooths LP into LQ, where Q is bigger than P, and he found the sharp rate. So this is, I'm using N now for the generator of the Ornstein-Uhlenbeck semigroup. That maps something in LP into LQ, okay? And the condition is e to the minus, this is the sharp condition. Okay, so as soon as t is that large, if you're doing in the infinite dimensional space, it's unbounded before that time, and then it's a contraction. Okay, and Gross conjectured that this was true for fermions. He proved a slightly weaker result, and I worked on this for a number of years with Elliott Lee, and before we finally found the proof, which was a good thing because in our earlier attempts to get at this problem, we found many other things. So sometimes being stuck on a problem can be good. So if we wrote it earlier, we would have missed maybe 3 other papers we wrote together. Anyway, so the point is I want to make here is that there's this really tight parallel between what goes on for fermion Gaussians and what goes on for Gaussians in probability space and what goes on for boson Gaussians. Yes?
Sorry, I'm just wondering, what do you mean here that the normalized trace is a Gaussian state? Like, you mean like if you take the trace with this?
Yeah. So let's say what this means for the x. So you take absolute x, which would be x adjoint x square root, right? Raise that to the pth power, and take the normalized trace to it. So those are the normalized Schotten p norms. Okay. And so that's what the p. That's what the p and the q here are. And so if you take any operator in this Fermi Fock space I described earlier, you apply this number operator semigroup, which is the Ornstein-Uhlenbeck. This is just for the regular trace. Then you have this contraction property. It takes you from LP into an LQ, where the Q is higher than P. Since it's a normalized trace, it's like you have a Holder inequality, right? And being in LQ, where Q is bigger than P, is stronger than being in LP. If you go off to infinite dimensions, it's much more so. So the same thing holds for Gaussians, the same thing holds for bosons, and it holds for fermions. And then it also holds for free probability, all kinds of things. There are all kinds of interesting applications of it. I mean, shortly after we proved this, Philip Bien did a free probabilistic extension of it using the same proof, essentially. Good. Okay, so the point I want to make is that, and then this was part of the inspiration for why Jan and I started to work, because then Felix Otto had developed this really beautiful mass transportation approach to understanding not hypercontractivity, but entropy production inequalities, which are almost the same thing for things like the Ornstein-Uhlenbeck semigroup. And so then, because of talking with Gross and earlier Irving Siegel, I was convinced that there must be something like that for fermions, a mass transportation approach, and this is what Jan and I began to work on here at IPAM. Okay, so that's it. Now let me talk about the boundary-driven systems. So what we're going to be studying is a situation where I have a Hilbert space, and it's the tensor product of two pieces. Okay? Now there are two pictures here, and the things in red belong to the HA, and the things in teal belong to the HB, and you can think of this as the bulk, and this is the boundary part. The boundary can be on one end or two ends. The second thing is what's mostly considered in the physics literature. People connect up one end of a system, a spin chain, to a hot reservoir, and the other end to a cold reservoir, and then you would expect to have heat flowing through it, and the recurrence in it, and so forth. We're going to be connecting things up just on one end, but to more than one site. And it's a non-trivial but interesting fact that you get currents also showing up in the steady state in that setting, as we will see. Okay, and moreover, we can do things, we can make these things local. So if I do my Brouwer and Weyl construction for the Jordan-Wigner transform, and I put my sigma z's starting on to the right, then when I put the w's in, they're going to undo all those sigma z's when I get to the red guys. So the red guys will be local on the red sites, separated from the others. Okay? Oh yeah, anyway, this is the thing we're going to look at. I've got a Hamiltonian. Let me go faster here, and here's the equation. So we want to look at this kind of equation, right, okay? So I've got a Lindblad equation with the Hamiltonian. The Hamiltonian's operating on the whole space, but the red and teal, the teal and red dots come in as the following. dA, we take a sigma, which is a Gaussian state on HA, okay, on this part of the factor. We take dA to be this canonical Gaussian generator associated to that state. So this is doing this Ornstein-Uhlenbeck process on the A part of the Hilbert space. On the boundary, the H is some Hamiltonian that's mixing everything up in the whole Hilbert space. So we're going to run a kind of dynamics that will be familiar to those of you who work on the Boltzmann equation. I mean, Francois Goltz is here, maybe others. In kinetic theory, the collision mechanism only affects the velocity variables. And then there's a streaming which moves things around in phase space, moving the X and the V's around, which transfers dissipation from the collisions into the whole of phase space. Okay? So we're looking at something similar here. I've got dissipation only on the A sites, and this guy is mixing it all around, and we want to know how fast this kind of thing relaxes to equilibrium, okay, and get a handle on that. This is a hard problem, okay, and it's outside the scope of the kinds of things that Jan and I looked at before, because this has no chance to be self-adjoint with respect to anything. I mean, it just is clearly, so it will not be, so this evolution equation, although the relative entropy with respect to the steady state is monotonically decreasing, it will not be gradient flow with respect for any kind of metric. Okay, so we need to leverage other things. Okay, so this specifies our quantum dynamical system, and we're going to let rho denote its steady state. Okay, so this is a non-equilibrium steady state, and what can we say about it? Okay, now we're going to also want to take this H to be a quadratic Hamiltonian so that it preserves Gaussian states. And this whole thing is going to at least take Gaussian states to Gaussian states, and that means we can do calculations on the covariance matrix of the Gaussian states to get some handle on what this thing is doing. Okay, so this is the reason for doing this, and these things show up all the time. So let me say a little bit about currents. if you have an observable K, this self-adjoint operator here, this observable is the time rate of change of K under H. And if you take the expectation of this with respect to a Gibbs state, the Gibbs state is of the form e to the minus beta h, then by an integration by parts formula, since h commutes with rho, this is just 0. So currents in Gibbs states are always 0. Okay? If you see a non-zero current, that's an indication of being a really non-equilibrium steady state. I mean, that means time reversal invariance is broken. If you change the sign of H, you change the sign of the current. Okay? So these are something that we'll want to study. Let me go back to do this thing. So the following is a model I've been looking at with David Hughes and Joel Leibowitz. David Hughes is a physicist at Princeton University, and Joel Leibowitz is everything. I mean, my colleague at Rutgers University in the physics and math departments, and is 95 years old and still amazingly active and sharp and sending email messages. Have you seen this new paper on the archive? I mean, I think he's right, it's relevant. And, okay, amazing. Okay, so here's what we want to look at. We want to look at this Lindblad equation. H is going to be this Hamiltonian, this quadratic Hamiltonian. This is called a hopping Hamiltonian. It annihilates a particle at J and creates one at J plus 1 and does the opposite thing. So the dynamics for this is particles hopping around on our lattice. Okay? And we can write this, we can diagonalize this HA as follows. So instead of writing it like this 2-by-2 thing, I can do a rotation by 45 degrees, and I can write this as the difference of two number operators. Okay? So the steady state for this ground state is this thing, which is a Gaussian state. So this is a pure state, but it is a Gaussian. And there's a canonical Mehler semigroup corresponding to it. And here's what it is. And notice these W operators. So this will be local on the two states. So this operator acts only on the HA spins, the two of them. It's not local to any one of them, but it acts on just on those two. So that's the generator. And the Hamiltonian has this form, which is this hopping Hamiltonian. Okay, well, this is the n by n matrix. It's just this thing, which you can diagonalize. This is the whole thing. And now we want to find the steady state. And you can find the steady state exactly, and it's not just for this single. The method could be done for any Gaussian on this two-dimensional space. So we just have to worry about, these four-dimensional, we just have to worry about these moments here. I mean, the L acts non-trivially only on these. On all the others, it acts in a rather trivial way. So the non-trivial action is going when you apply the L dagger to these four guys that live out on the end of the chain in the HA. Okay, and let's use the following notation. I'm going to write the moment matrix of my steady state. We're going to put m's down the diagonal, and it's got these zij's up in here. And by these calculations, you can work out what the action of the Lindbladian on m is. And here's what it is. So notice it's a whole bunch of zeros. So the first two rows are non-trivial. The first two columns are non-trivial. Everything else is 0 because the Lindbladian only operates on those two sites. Okay? Then there's also the Hamiltonian thing. And what does that do to the m? Okay? What it does is you take a state ij, you take the sum of the entries above and below, and subtract off the two entries which are on the two sides. Okay? That's sort of like a Laplace type operator, not exactly. And so you can write out what that thing is. And now we begin to do an analysis of this thing. Okay? So this continues down to the side of this thing. And suppose we have a 4-by-4 matrix, then the y45 is going to be 0. So this is equal to something 0, because you see, my equation is this equation, and this guy has a big block of zeros down in here. So this commutator term has to be 0 outside of these first two rows and columns. So if y45 is 0, that means y34 is 0. If y34 is 0, that means y23 is 0. So you can chase things up the diagonal like this. Okay? So let me skip this because I'm going to run out of time. But you do a bunch of analysis on diagonals. Okay? And this summarizes some kind of stuff you get. And what I wanted to notice here is you first observe that you're going to have non-zero imaginary entries, the y's are the imaginary entries, they can only be in the first row. And second, from this guy, once you know what the y's in the first row are, that tells you what the x's are in the second row. So once you've got the first row, this gives you the second row, and then there's this Laplacian type thing, which makes it easy to piece the whole thing together. So we can actually solve this. This took a bunch of time to do it. Okay, there are more formulas here that you can see, but in the end, here's the example for what you get for 7 by 7. Now, notice that this thing has a 2 gamma to the 6, okay? So these are all C and 2C. So you have 1/2, 1/2, 1/2. So all the diagonal is always 1/2. And in the large gamma limit, this is what the thing looks like. So as you take gamma off to infinity, this is what the covariance matrix for the steady state looks like. But you can compute it for all of the gammas. Okay? And you can take the large n limit. And so there are a bunch of calculations of what the steady state is. And the steady state actually shows real currents in it. So there are these currents in the steady state. That's because we have these imaginary things. Let me draw them up here. You see this guy's imaginary, so that's going to be time reversal non-invariant. This guy's imaginary, and their imaginary is going on down every other term here. So this is the steady state. It's a real NESS. Its time reversal invariance is really broken. And now we want to know how fast do you approach the steady state. Okay? Now, there aren't so many models you can write down exactly what the steady state is. But once you know what the steady state is, this is very helpful if you're trying to understand how you approach it. So we were quite happy when we got to this point and could say what the steady states were. And now, just to wrap up quickly, this has to do, we're going to look at this in the large gamma limit. Okay? So in the large gamma limit, things simplify. You've already seen back over here that, I mean, in the infinite gamma limit, the steady state gets a lot simpler. There are all these entries which are smaller on the off. So this simplifies. In the physics literature, this large gamma regime is known as the quantum Zeno regime. This quantum Zeno effect was first pointed out by Alan Turing in 1954, which is the year in which he died, suicide in fact. And what he observed was this. Here's the quote from his book. There's no paper because he died before he could write a paper. If you make repeated measurements, you project onto an eigenspace, and you get the same one if you're in the eigenspace. So if you keep measuring something, you freeze the state of the system. Repeated measurements keep it from evolving. So he observed this. He discussed it with another mathematician at Cambridge. They wrote it off to some physicists. Physicists poo-pooed the idea and said you can't measure instantaneously, Okay, he was ahead of his time, as in so many other things, because now you can Google quantum Zeno effect and you find 1 million papers. Okay, so this large gamma limit. Now the thing is that this dissipation operator is in some sense doing a measurement. All effects of observation in quantum mechanics are coupling a system to an environment. And so you get the same sort of thing when you couple a system to an environment. And this is sometimes called the watched pot effect. The watched pot never boils. If you keep looking at it, you just freeze the thing. Okay? So we're going to be looking at this system. The K is the evolution, and it's got a 1 over gamma because I've rescaled the time. So we're going to make this unit order, and this has a 1 over gamma. Okay, so there are two things, and I've got to wrap up in 2 minutes, so let me tell you the main gist of this thing. There is an important contribution made by Zanardi and Venuti, two physicists in University of Southern California, and what they showed was that, indeed, if we take these projections, this is the projector onto the ground state of D, okay? And this is the orthogonal complement. So now the D, what is this D? See, the D is the dA tensor the identity. So the things that this is projecting onto are the things that are sigma on the HA space, tensor anything you want on the right. So it's a huge space. The range of this PA is not just sigma, not just D ground state, because this degenerate thing has a huge set of steady states. Okay? Now the leakage out of, okay? So what they showed was the leakage out of the range of P is very small. It's of this order here in gamma. And so this is a formula for it in the trace norm. So you relax to the steady state manifold and you move along it, okay?
Is there a t missing on the right somehow?
Excuse me?
In your formula, is there something missing on t on the right? Don't you expect that?
No, so it's uniformly in time.
Oh, uniform.
Okay, and after a small, because we're assuming that the initial layer has been done. So see, I'm already assuming that the P naught of rho equals rho. So I'm already in the steady state space, and then this theorem says you never leave it. Okay, and so that's why there's no t. You just stay there uniformly in time. Okay, now that means that this evolution looks almost like this. It's sigma times rho b of t, and we have uniform control on the errors. What can you say about the evolution of the b of t? Okay, now this was studied by another group of 4 people. Well, there's a corollary of this thing first. The corollary is like the Zeno effect. Things are moving slowly. So the time rate of change is like 1 over gamma. How does this b of t evolve? There's another physics paper by Popov, Essink, Prasilia, and Schutz, and they do the following thing. So we define operators A and B as the following. Now this is the K, remembers the commutator with the Hamiltonian. This is our projection. The K is the commutator with the Hamiltonian. The slide doesn't say what S is, but it's the generalized inverse of the D, the dA. Okay, so this is where that shows up. I mean, of the D, sorry. So the dissipation shows up in this term. And then they proved by doing a Dyson expansion, Duhamel, out the second order, that this rho b of t satisfies this plus the O gamma to the minus 3. Now, if this weren't here, this is just the Taylor's formula with remainder out the first order, which would say exactly that, let me look at this thing. This would say exactly that rho b is e to the t, a plus b. Okay, good. Now here's the surprising thing. They showed that this a plus b is a Lindbladian. So this is a second Lindbladian. This is a Lindbladian on the smaller Hilbert space. So this is an effective Lindbladian for the long time limit. Notice I've also put a gamma in over here. So what you have for the large time in this system is you have a slow evolution, which is mostly the unitary with this thing, and now the gamma, instead of being upstairs, is downstairs. There's a small dissipation, and you're dissipating slowly under this thing. There are explicit formulas for the Lindblad operators in this guy. It's not just some abstract thing. It's a computation of this proof. You can write it down. And so the problem is, in this paper, these guys did an even rougher version of this. They just truncate the expansion, and knowing that you have an approximate solution doesn't tell you very much for large time. So the right thing to do, what we are working on with Joel and David Hughes, is a proper derivation of this thing. And that's not hard to do because one can apply Davies analysis, which is good for long times, and justify this equation. And then we want to study how fast this thing is decaying and relate it to the original evolution. And this should give us some information into whether this dream is, whether the answer is yes or no for the dream. So this is what we're working on, and I think I'm more or less on time, so thank you very much for your attention.